All right, how's it going, everybody? We are here. It is Friday, February 26th, and we are going to be talking about more Newton's method today. We're going to be looking at Newton's method for systems of ordinary differential equations today, rather than individual differential equations. So we're going to be writing only Python code today since we're not learning any new math. We're still just using Newton's method, but we want to see some of the things that we got to be careful with associated with systems as opposed to individual differential equations. So the couple things that we're going to be exploring today are going to be one, how do we want to alter our code so that we can make Newton's method work for a system? Because now we have two dependent variables that we want to be updating, and there's one small technicality we got to be super careful with that. Another thing that we want to think about is that when we look at our systems of differential equations, we know that we've been looking at some of our graphs being produced, right? When we go to our slope field graph or over here, we know that when we've been looking at the systems, we've been looking, one, at our two dependent variables, x and y, graphed parametrically in terms of t. We've also been looking at individual graphs. Okay, graph this thing. Come on, what are you doing? Oh wait, I gotta click on a thing. Individual graphs of x of t and y of t on the same plot. I'm hoping that you remember our intense dissatisfaction about the non-matching y-axis right here. We're going to fix that today. So we're actually going to come up with some better plots, and we're also going to look at producing these tables of values that we can look to see when we achieve particular values potentially of interest to ourselves. The last thing that I want us to be thinking about here is that when we looked at some of our examples, it wasn't really clear if there were trajectories in this plane right here that were potentially maybe looping back on themselves. Were they supposed to be getting back to where they started or not? That's a kind of a tough question for us to be answering here, but we want to kind of look and see if we can kind of arrive at some more information relating to that today. So today, I'm intending to be quite a bit shorter than the previous video, but we are going to be, writing some more Python code here and producing, importantly, two different graphs today rather than just a single graph of a solution. So let's go ahead and get started here. That's not my one. Here's my one. So Newton's method of systems of ordinary differential equations. Last week we wrote the Python code to use Newton's method to approximate solutions of single differential equations. Today we'll step that up to consider systems. Most of the computation is going to be similar. We pretty much just have to do everything twice since we now have two differential equations. Like I said, though, there's one tiny technicality that's very easy to gloss over that we want to not gloss over. So we're going to be real careful about one small thing here. We do, however, have different graphs we're interested in producing. So today's focus is slightly less on Newton's method, since you already know it, and it's literally just do y equals mx plus b a whole bunch of times. And we're going to focus a little bit more on the visualizations, on the graphical production here. You guys have seen in your homework from last week that I asked you to produce one graph with only the basics in there. This coming week will be a lot more about producing the appropriate graphs here. So what I want to start with is I want to come back to this graph of our rabbit and fox populations right here that we've started with, right? This was our first system that we ever really considered right here. And we want to look at these graphs and we want to see some of the, I guess you'd say, flaws associated with Newton's method. And I shouldn't say it's a flaw because Newton's method is never intending to give us exact solutions. It's an approximation technique. But we want to see what are the weaknesses of it, I guess. Where are the ways in which it can lead us astray? Right? So there's two important things that we saw when we have previously examined the system. One, we identify that there's equilibria at 0, 0, which I can just look at. I can see that from visual inspection. That is R and F are both 0, then drdt and dfdt are both 0. But the other thing is that we did some algebra and we also found that 10/9 and 5/3 are also equilibria locations right here. Right? And by the way, just real quick, if you guys want to see, notice that these are markdown cells that I've got this stuff written in again, right? In Jupyter Notebook, you can do your code or your markdown cells. If I change it to code, it's got a bunch of things in here. It's trying to interpret a bunch of these values as Python instructions and stuff like that, and that doesn't make any sense. So switching this to markdown, I just wanted to kind of show you this very briefly in case you care about mimicking my LaTeX code that I'm doing here. I want to show you one kind of tiny annoyance with this, by the way. If I put these two things, and so this is just, this is kind of bonus little stuff about how Jupyter and how LaTeX work right here. As I kind of showed you guys last time with the quad for a horizontal spacing of essentially a tab inwards, LaTeX is really weird about spacing things. And so here I feel like I'm going to get the fraction dr over dt equals this equation, and this fraction df dt equals this equation on two different lines. But notice if I run my code as it is, it shows up with them on the same line right here. Technically hitting enter apparently isn't enough. This is like my least favorite thing about LaTeX right here. It matters that you do space, space right there, and now they are on two different lines, but they're even still really close together, and I don't like them that close together, so I'll double click again, and now I'll just hit enter right there, and now they're actually like lightly spaced out. But if I did a whole bunch of enters like that, it doesn't do additional spacing right there. We would need an extra command. I think V space for vertical spacing would be a LaTeX command we could use to get more spacing in there. But I love the ability that I have to write math inside of these Jupyter notebooks like this, and every fight that I fight is always a spacing-based fight in here. It's my least favorite component of this guy right here. Notice another small thing right here. This thing has list functionality sort of built in. If you do numberings, it has to be with dots right here. You should notice that this is in blue. It's interpreting this as like a numbered list, and so notice it's like slightly indented, and it will like follow like appropriate indentation for that right there. That's a nice little built-in feature there as well, in case you're interested in kind of writing some slightly nicer things in Jupyter notebooks here. So let's get started. What I want to do is I want to be able to essentially imitate the graphs that we would have seen at the Bluffton website over here associated with this guy. I want to do the Newton's method for this guy. So what you're going to see is a bunch of code that you absolutely should be recognizing from the previous video, but we're just going to double up on a bunch of things like that. And as I have said twice now, there's one careful technicality that we really have to watch out for with our more than one differential equation, and I will point that out at length when we arrive at that right there. So what's the first thing that we want to do here? Well, the first thing that we want to do is we want to remember we're going to need extra help other than just the core of Python, right? So the two external libraries that we want to use are NumPy to help us out with our numerical calculations. That'll get us things like our exponentials and our sine functions. It's also going to give us some extra list making capability. That's going to be what we're going to use it for here today. The other thing is we need our plotting library. That's our matplotlib.pyplot. So let's go ahead and it's in general, it's just very typical in any Python file that you write that regardless of where you use those functions, it's generally considered like best practices for your imports to always be at the very top and to be all collected in one place. It's just one of those things that helps the other people read your code more easily here. So I'm going to do our usual import NumPy. And I don't want to have to call it NumPy every time. I'm going to call it NP. So I'm going to give it an alias right there of NP. I also want to import matplotlib.pyplot, the sub-library. The pyplot library is the library within the matplotlib library. That's pretty obnoxious right there. But we're just going to give it the abbreviated name as PLT. That's its alias is PLT. So that's what we'll use for all of our graphing purposes. So I will shift enter, or click the run button to run that cell. And again, if the number shows up there, then I know that it did it. And by the way, I don't know, like you should watch this for a second and see that an asterisk will be sitting there for a brief split second. Yeah, and then the one came up. You can literally visually see how long it took NumPy or took Python to like bring in that known knowledge right there. It wasn't zero amount of time. These two libraries are kind of massive. This has been a huge mountain of work that hundreds and hundreds of people have done to like put all the parts into these things right here. So that little smidge of time right there, that was Python running like a couple 100,000 lines of code in the background of like kind of like learning all the knowledge of those libraries right there. So a lot of powerful stuff gets brought in with those easy import statements. So what we learned from last time is that we need to do things like define our functions of interest. And in fact, what I'm going to do for myself right now is I'm even going to go in here and modify this. I'm going to say this is my f of r f. Maybe a bad naming choice right there, but that's okay. So lowercase f is that function. Capital F is our number of foxes right there, right? So I'm going to call those things so that we don't get any confusion. Lowercase f is the name of this function. Lowercase g is the name of this function. Capital R, capital F, that's our counts of rabbits and fox populations. And in my mind, these are like in the millions, right? It's like if you get the number 3, that's 3 million rabbits or whatever out there. So I'm going to define the functions associated with our differential equation. Remember, in Python, the pound symbol right here makes a comment. So this is not code that gets evaluated. Everything after a pound sign on any line is just for humans to read, not for Python to actually run that code. So I want to define my new function. Remember that it's black right now because it has no special association with DE. As soon as you see DEF, Python's like, ooh, that's a special word that I know. That means that he's about to define a function. I want to define exactly these functions exactly as they're stated right here. So I'm going to define f of r, capital F. Notice that f is in blue. It's recognizing that that's what I'm going to be using as the name. And what I want is if the inputs are the number of rabbits and the number of foxes, then the output, the value that should be returned from the function, another special Python keyword should be 2 times r. Remember that 2r won't cut it in Python. Python doesn't know what 2r is. You have to tell it 2 times the number r minus 1.2 times r times f right there. And capitalization is going to seriously matter here. I like to use f and g as my generics. We've got r and f as rabbits and foxes. I think that we can handle a couple capitalizations here. We're pretty smart people. The other function that we're going to need that's going to go along with this is our g of r comma f function right here. And I'm kind of keeping my screen so I can see the math and the Python on the same line right here. What am I going to get out from this guy? We are going to return negative f plus 0.9 times r times f right there. So I think that I have produced the values that are associated with these guys here. Last time we checked this. So remember that we need to run this cell so that it learns these functions. We haven't run this code yet, so I'm going to shift enter. And now I see the number right there saying this cell has been run, so it knows these. And one thing I'm thinking is it's kind of weird for me to check this since we don't have an explicit solution. Check. We don't have explicit solution to compare against. But we do know where the equilibria are. So to check this guy, what I'm going to do is I'm going to ask it for f of, and remember, this is our two equilibria locations that we found. Or sorry, our essential equilibria locations at 10 ninths, 5 thirds. Let's see if that works out here. 10 ninths, comma, 5 thirds. And I want to do that both for f and for g and see if we get 0, 0 as I'm expecting. So this says plug 10 ninths, comma, 5 thirds into the lowercase f function. Plug in 10 ninths, 5 thirds as the rabbit and foxes for the g function. And what do you know? We're getting 0, 0 for dfdt and drdt. So that gives me a little bit of confidence. A, that we did our algebra right a couple days ago with the 10 ninths and 5 thirds, and B, that the functions that we just wrote do seem to be imitating that because we're getting no change and no change for the rabbit and fox populations out there. All right. And it's always, and like the whole point of this Jupyter Notebook setup is to like, that we can stop and run a little bit of code, check some stuff, write some English. Like we don't, the whole point of this is to get away from the style, the old school style of writing code where it's like you just have to write a monster program and then run it and debug it and beat your head against the wall. Do little things at a time. Every time you write a little bit of code, be like, did that work the way I thought it did? Let's see some outputs from it. Nice and easy. Right? So we did a little checking right there. Right? So next thing we want to do, and again, I'm just mimicking the style of what we did last week, is we now want to define the parameters that are associated with this guy right here. What are like the constants that we're going to be using? Well, we need to define some, let's initialize the parameters we want. So a couple parameters that we're going to want are initial conditions. Now, I'm using capital R and capital F as my rabbit and fox populations, so therefore R0 and F0 are going to be our initial condition values right here. And I am doing a super special thing, by the way, right now. For those of you that have minimal programming experience, this shouldn't seem special to you whatsoever. For those of you that have a lot of programming experience, you should be like, wait, how is this really working right now? So here's a kind of cool thing that Python does that most languages, and I say most, like 98% of languages are not down with, which is simultaneous assignment. Right here, I am saying assign to R0 and F0 the values of 1 and 1. And we can even make this like a 1.5 to make a distinction. We're going to go back and change those initial conditions eventually anyway. But this simultaneous assignment right here, this is like, it's not unique to Python, but pretty dang close. There's very, very few languages that are okay with assigning multiple things in a single equal statement right here. And it turns out that this is going to be highly valuable to us here in about 5 minutes. So hang on, and I'm trying to just show you that it works that way. You can just as easily put these two assignments on their own lines right there, which honestly might be a little bit better for when we go to modify them later. But this type of simultaneous assignment does in fact work, that then I can ask for just R0 right here and it knows that it's 1. I can ask for just F0 here and it knows that it's 1.5. So that's pretty nifty. And again, if you have no programming experience, that probably doesn't feel that's crazy to you at all. The more programming experience you have, I've seen lots of like pro coders that are like, wait, are you serious? And get pretty worked up about just that small bit of functionality right there. So kind of cool. The other thing that we know is that our goal here is to produce graphs. And what we've learned about our graphing library here is that what it wants to take in is a list of X values and a list of Y values, and it will correspond those things to each other, plot them as ordered pairs, put a curve between them. So what I know we're going to need to come up with is things like a list of T values, time values, a list of rabbit populations, and a list of fox populations. Those are 3 lists that are going to kind of hold all the values that we're determining over the course of this thing right here, all right? So it seems to me like we want to come up with a T list. So lists to hold the values. We compute. So I need a T list. I need an F list. Do I want to do I don't want to do, okay. I'm going to do some weird things here. R list and F list. I feel personally highly uncomfortable about using capital R and then a capital L as my next letter right there. But I don't want to get any uppercase, lowercase confusion here. Capital R, capital F are our fox rabbit populations right here. So I'm just going to stick to that notational convention. And all these things, we're just picking a name, but we want to pick names that are going to be easy for us to be consistent with. So I think it's a bad idea to sort of change your naming convention partway through. So here's the place where we're going to use the NumPy library to help us make some easy lists for ourselves, right? What I kind of, oh, sorry, actually, I skipped over a chunk of things that I want to do right here. We need to make a list of time values that we're going to see, but what we haven't discussed is what we want our step size to be and what the total duration of time is. So we're going to define these values ever so slightly different than we did in the last video here. And so what I'm thinking to myself here is, we're going to define some time parameters. So I want to give a step size, delta t, and I don't know, let's make that 0.001. This is my step size. And the other thing that I'm going to want is the total time. I'm going to call that capital T because it's the total amount of time. So this says do steps of size 0.001 and do it for 10 total units of time or something like that. So let's just set that to a number like 3. So in this case right here, it looks like we would have to do 1,000 steps to get to 1 unit of time, and we're going to do 3 units of time. So this setup right here would give me 3,000 Newton's method steps that we're going to end up doing right there, right? So we're going to do step sizes of 0.001, and we're going to do that from a time 0 out to time 3. So 3,000 total steps will end up occurring out there, right? So what I want to do now is I'm going to build this information a little bit differently than I did last time, right? What I just want to get is literally just what are those steps going to actually be out there. So I'm going to use the NumPy library to smartly build a list for myself. Here I'm going to say, hey, NumPy library, NP. I want you to build for me a linearly spaced list, and I'm going to give it the instructions as to how I want that list to be built. So linspace is going to create a linearly spaced list for us from the NumPy library. It's a function, so I'm going to use some parentheses right here. And this linspace function takes in 3 values. It takes in start, stop, and step. All right. So, it takes in start, stop, and number of terms. Okay, I almost did that wrong right there. So where are we going to start? We're going to start at time 0 every time. Where are we going to stop? We're going to stop at time capital T every time, which we currently have set to 3. How many terms should there be? Now, how did I come up with that 3,000 number a moment ago? The way that I came up with that 3,000 number really is I just did 3 divided by 0.001, right? Remember that this is just a calculator too. That's fine for us right there. So I need a number of terms, but I need this to be as an integer. And you should notice that anytime you literally ever do division in Python with a single slash right there, it's always going to give you a decimal on the other end. However, if I wrap this up with int for integer, or the int data type, it's going to give us back the integer format of that guy right there. So that's exactly the type of computation I want to do, but I don't want to hard code these numbers in there. I want to use the t and dt that I've defined above. So I'm going to do here an int of, it looks like that was our capital T value divided by our dt value right there. Now, the other thing that we've learned here is that Python is a little bit weird about its terms that it uses here, where we saw that if we do things, I'm pretty sure we saw this, right? When we do like list range 4, it gives us the first 4 numbers that Python knows, 0, 1, 2, and 3. So it's really always got this sort of like off by 1. This doesn't go 1, 2, 3, 4. It goes 0, 1, 2, 3. There better be 4 things when I say the range 4, list range 4. I want 4 objects. But to Python, the first number is 0. So it turns out that we're going to be helped by putting a +1 on the end out there. So it actually gets to time 3 instead of getting to time 2.999. Because if it builds 3,000 objects starting at 0, the last one would be 2.999. I want my last one to be 3. And so there actually needs to be 3,001 objects to get from 0 to 3, counting by 0.001. That's our fence post problem right there. If you want to build 5 pieces of fence, you actually need 6 fence posts to hold up all those pieces of fence. That's what that +1 is doing right there. All right. So what this is going to do is it's going to create this linearly spaced list for us right here. And let's just see, and again, you can play around with all this code right here by just kind of like seeing how it works. Let's just do an np.linspace from 0 to 5, counting by sorry, we do our start and stop and number of terms. If I did 50 terms right there, then you can tell that it didn't just give me 0.1s, right? But if I do 51 terms, we get all the 0.1s because there needs to be 51 terms to actually get the 0 and the 5 included right there. So it's always got that little bit of an off by 1 error. It's not an error, it's just the way that Python is built. It turns out that indexing based at 0 makes more sense than indexing based at 1. It was a smart call, but it seems weird when you're first getting used to these kind of things right here. So that's sort of my example line of code that sort of justifies why that +1 belongs in there. We need 51 fence posts to build the appropriate 50 steps that we want to build between them. All right. And again, the whole point of Jupyter Notebooks is you can stop and play around with one line of code at a time to make sure that this is going to do things that we want. I don't want to see an output that has 3,001 terms in it, so I'm stopping and looking at a smaller example and confirming that it behaves the way that I think that it's behaving right here. Started at 0, stopped at 5. 51 terms actually gave us a step size of 0.1, not 50 terms, because we wanted to include both endpoints right there. Okay? So we've got that linspace function is helping us build a list. And notice, by the way, it's calling it an array instead of a list. That's because this is a NumPy specialty list right there, but it's behaving like a list. That's a technicality we don't need to worry about. Now, we don't have any values that go in our R list or in our F list yet. What we did last time is we kept on adding things onto the list. We kept on appending it to the list by saying, the list only had 1 item. Let's stick a new item onto the end, a new item onto the end. We're going to do this one in a little bit of a different style here today. What we're instead going to do is we're going to build a list that has all the number of slots already in it. So rather than going from a list of length 1 to a list of length 2 to a list of length 3, we're just going to build an empty list of length 3001 apparently right there, because I know that the length of T list right now, and in fact, let me just do this, should be 3001. So I can double check this. Len T list. I got to run this guy right here. The length of the T list, 3001 objects, exactly as I thought there was going to be to get us from 0 to 3 out there. All right. So what I want to do is I'm going to build essentially an empty list that has 3001 slots in it. And instead of adding a new item into the list, we are going to overwrite one of those blank spaces with the thing that is actually going to belong in it. So visually stop and picture this for yourself. Rather than making your list be of the length of the number of terms that you currently know, we're going to give it all of the length that it should have, 3001 blank spaces. We're just going to make them all zeros. Then as we compute the ith value, we are going to overwrite that 0 with the actual correct value that we have computed, rather than building the list of adding onto its length every step of time. There's actually some really smart efficiency things that are going to go on here that are going to make this computation go much faster because we do it this way. I just think it's better organized to do it this way right here. And so what we're going to do here is we are going to build empty lists of zeros for the R list and F list, which we will replace with their correct values as we compute them. So the NumPy library is going to give us a smart list constructor that's going to do this also. It's called np.zeros. I think is it zeros with a, yes, it's zeros without the E. I guess I should mimic that right there. I feel like that's like a American versus British spelling kind of difference right there. I'm not really sure. I think that maybe both of those are correct. I'm not sure. Anyway, the point is, for the zeros thing, and we can check it out right here. Let's just do one. np.zeros 6. What is it going to give us? It's going to give us a list that's got 6 objects in it that are all just 0, right? And so again, we're building our full-sized lists, but it doesn't have any meaningful numbers in it yet. And by the way, it's also typical to do ones. The zeros and ones are 2 special list constructors. There aren't constructors for like 2s and 3s, but I could just do this like times 7 and it will make it a list of 7s right there, the 1s right there, something like that. So some smart things that NumPy really helps us handle right there very carefully, which is pretty cool. So I'm going to do numpy.zeros. Now what I know is that later I'm going to want to make a T versus R graph and a T versus F graph. And so what I need is those 2 lists are going to have the same number of objects in them, right? So if this list had 3001 objects in it, then this one better also have 3001 objects in it. But the fact that there's 3001 objects in this list is based on T and DT, and I really only want those to be the numbers that get changed. I don't want to like type in 3001 right here. So I'm just going to say, how long should the list of zeros be? And I'm going to say, well, I don't know, however long the T list is. I'm going to get the length of the T list, and that's what I want the length of the zeros list to be for R and for F. So in fact, I'm just going to copy and paste this down. So we're building 2 blank lists right here that we're going to overwrite one by one those zeros and fill them in with the correct terms. That's going to be our slightly new like strategy for building our lists here today. All right. So we should now have a T list, an R list, and an F list. And what I want to double check, because again, the plotting library is going to get super mad at us if we give it like 20 X values and 30 Y values. It's going to be like, well, what do I do with 10 Y values that are unassociated? And it won't build our graph. So my quick double checker to make sure that I'm not crazy right here is let's look at the lengths of each of these guys and see that we're in good shape. And all 3 of them have length 3001. So I feel pretty good that we have lists of the same length so that when we build these as like columns that are like ordered pairs, every X value will have a Y value, or every T will have an R, or however we're thinking about this here, all right? So the other thing that I know is that we've actually already picked out what we want the first value in each list to be. So let's go ahead and set that to be the case. All right, so we defined some initial conditions right here. Oh, right here. By the way, if you're seeing my screen do this like slide up, slide down thing, it keeps on doing a very annoying thing where it auto saves, but it brings up a little like notice that it's auto saving every like 60 seconds. And that notice takes up room up here. So it moves the whole screen down so that it can put auto saving at the top. And then when it's done auto saving, it goes away again, and it drives me insane. And so that's why my screen is doing this like shift up, shift down every like 90 seconds or whatever it is out there. So what we want to see is how does this work here, right? And so I'm going to maybe do a little bit of an example right here just to show you how a little bit of this code works. If I make a list and I call it X, I can make this list 1, 2, 3. Then that's my X list, and I can ask it for X, and I can say, hey, what's X after I've defined it? And it says it's 1, 2, 3. What I can do is I can say, hey, let's make the ith value of X like 9, right? And so I might say X0 equals 9. And now what does the X list look like? Well, it went to the index 0 term in the X list, the first term, X sub 0, and it overwrote it with 9. So this is my way to overwrite a value, is to say at index 0 within the X list, make that number 9 instead of whatever it was before. It overwrote the 1, and notice that now when we ask, hey, what's our list look like? It says, well, now it's 9, 2, 3, stuff like that. Remember that we start at 0. 0 is always our first location. 1 is our second location. X sub 1 is the second term in our sequence, stuff like that. So this is how we're going to overwrite those things. So what I want to do is I want to say, hey, let's take the R list. At the first location, the 0th index, what should be there? What should be there is whatever we've defined R0 to be, our initial value of R. We defined it up here to be 1, and we're going to change that. That was an arbitrary selection. Very similarly, we want in the F list, we want the thing at index 0. Yeah, autosave, to be F0 right there. And so now we should have 1 and 1.5 as the first items in those very, 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 very long lists, right? And we can verify that as well. And in fact, let's do that. And I want to show you one other cool slicing thing we can do. I know that if I look at our list, oh, okay, that's interesting. So NumPy displays its specialty arrays differently than Python displays generic lists. I'm very happy with this ... but what you can see is with the R list, it does start with 1 and then just have zeros forever. The F list does have 1.5 and the zeros forever because that's what R0 and F0 were that we defined up there. All right. So I was going to do saying, give me the first 10 things, go up to 10, and then it will give me the first 10 things, or we could do go up to 5, and it'll give me the first 5 things. So that colon does the up to right there. So just some other list slicing to get a sub list out of a list right there. So I can see maybe just what the first terms look like. This is a really useful thing if you're trying to modify a list that has 1,000,000 items. You don't want to print 1,000,000 items out onto your screen. You just want to say, show me the first 20. This is a way that we can do that easily right there in Python. All right. So we've defined, I think, all of our like setup stuff. We've defined some initial conditions. We've defined our step size and total time. We've built a time list where these are just the times we're going to use. We now know all the times that are going to get used along the way. And by the way, maybe we can look at our T list real quick here. Notice, by the way, NumPy using some scientific notation right there. This is like your TI calculator giving you outputs here. That is 0.001 right there because we've shifted decimal several places to the right. And by the way, I actually think that Python handles this natively. Like, yeah. So notice it actually handles by default. This isn't NumPy specialty anything. Python's cool with using your scientific notation with ease, which I think is actually really surprising to me that that works out to be interpreted as the number 2.5 times 10 to the 5th. But again, other nice little things that Python does that are actually kind of cool for us. Kind of nice right there. So we can see that our list does start at 0 and does go out to 3 and is clearly counting by 0.001 as we interpret it as 1e. And in fact, I mean, honestly, if you don't like that notation, just convince yourself that it is in fact 0.001. You can just run that to evaluate that with the e right there. So we've built these lists. The T list actually has the times that we're going to use. The R list and the F list are essentially empty lists. They're just lists of zeros, and we are going to one by one overwrite those zeros with the values that actually belong within their lists. We've already overwritten the first value in each list, the initial condition, where those things actually start at right there. All right. So now I believe that we're ready to actually do some Newton's method things here, right? So we're just going to do Newton's method, and we remember what that looks like from yesterday. But there's going to be a really important thing that I want to warn you against. So what I'm going to do right now is I'm going to write code that's going to be almost correct, but it's actually going to be incorrect. So I'm going to write the wrong code now, and we're going to tweak it in the most technically tiny way to make it actually be exactly what we want. All right. So just be aware that I'm going to write something that's slightly wrong right now. It's going to be very close to right, to where you can still type it right now, and we'll just be able to modify it in very slight ways. All right. So here's what I'm thinking to myself. What I want to do is for all of the times, except for time 0, because time 0 we already handled right there. So I want to say here, do Newton's method, but start at time t equals 1, since time t equals 0 was already handled with our initial conditions, right? So we already did time 0, right? It's sitting right there. This line of code that's highlighted, that's us saying at time 0, we already know what's going on. So our next move is to use the time 0 information that we already have to compute what's happening at what we would refer to as time 1, which we know is really t equals 0.001. Right? Okay, I need to phrase this slightly differently. Time index 1, because time index 1 is really that 0.001 is actually what the t value is that we're taking on right there. So here's what we want to do. We want to do a for loop again because we want to repeat that updating over and over and over again, right? So here's what I'm picturing my for loop happening. I'm going to say for, I'm going to call I for the index. For the index I, in the range, I want to start at the first index. That's what I just said right there, the first time index. And what do I want to do? I want to go all the way up to the length of the t-list as my final index out there. The length of the t-list is 3001, and so that's how far out I want to keep on doing Newton's method, right? So this is going to say for every time in the time list is sort of like what we're saying right here, but we're referencing them by index, not by the time. And so I'm going to say, by using this I indexer, we are referencing not the actual times, like 0.001, 0.002, 0.003. Indices in the t-list. So our above list would correspond to 1, 2, 3, right? Because our original time should be 0 as the first one right there. So these correspond, right? Index 1 has time 0.001. Index 2 has time 0.002 within the t-list, right? So what we want to do is we want to update what is existing in the list at that time for the R list and the F list. So I'm going to do my R list. Well, what's going on in the R list is that we want to overwrite what is at index I. So I is going to start at the value of 1. So I'm thinking to myself, at the index 1 in the R list, which I'm using the variable I to hold that as, I want to overwrite the 0 that's at index 1. Remember that index 1 is the second slot, index 0 is the first slot. I want to overwrite that 0. So I'm going to do exactly what we did right here. I'm going to say overwrite index 0 of that list with this value. I'm going to overwrite the value at the R list at the ith value, where I is going to take on all of those numbers right there, one by one. And I want to overwrite it with what Newton's method would tell me to overwrite it with, right? So how do we do Newton's method here? Well, how we do this is we reference our previous value, right? So this is like me coming up with y sub I. I want to say, we'll start from y sub I minus 1, also known as R list, I minus 1. That's my previous value in the R list. And it's known, by the way. It's known because in our case, we're starting with I being 1. So this will be the 0 index value in the R list. It's literally going to be the initial condition. That's where we start building off of right there. What do we want to do? Well, we want to grow this thing, and we want to grow this thing by the f value. Remember that the f, the lowercase f function, is what modifies our rabbit values right there. That's our definition right there. So we're going to get our rate of change from that lowercase f function. So f of, we know that that lowercase f function takes in a rabbit population and a fox population. Again, if we're trying to compute what's happening at time 1, we use time 0 information. So it's the I minus 1 again is what we want to use right here. So the rabbit population at the one previous time, we also need the fox population at the previous time. And for how long would we like to travel in this direction as defined by our differential equation? We would like to do this for dt units of time. There we go. That's going to be our update. That is Newton's method right there. You should just be thinking of these bracket i's and bracket I minus 1s as really just like subscripts, right? This is saying y sub I equals y sub I minus 1 times the differential equation evaluated at the previous time, and do that for the length of our time, our step size, that 0.001. it seems like to do our Fox update, we just want to do the exact same thing. So I'm going to do this right now. I'm going to copy and paste this because we're doing almost the exact same thing. We just got to change some R's to F's and we should be good. And then I'm going to tell you why this is not going to quite be right here. And it's for a math reason, not for a Python reason. But Python is what's going to help us fix it. So I'm just changing R's to F's here. I need to change my lowercase f function to my lowercase g function. These stay because the g function also takes in r comma f, right? G takes in r comma f. So these stay where they are right there. And we're doing it for delta t times. The only thing I changed was just those two f's right there came from those two r's right there. And the lowercase f function became the lowercase g function. So this feels good to me. And by the way, if I run this, it ran. It didn't give me an error message. It was happy with this. But this is a little bit wrong. And I want to show you why this is going to be a little bit not quite what we want right here. The reason why this is going to be a little bit off from what we want this to be right here is this. What this is going to do is first, it's going to update the new R value, right? So it's got a newer R value right there. What it's then going to do is it's going to update F based on its most recent R and F values. But the R values have already been advanced in time by 1 delta t, whereas the F ones have not. So when we do this, we're sort of using 1 unit of time associated with the R values, but a different unit of time associated with the F values because the R's already got updated. What we want to do is we want to update the R and F's at the exact same time to make sure that they're both referencing the appropriate location in time. All right. So what we need to do is we need to do a simultaneous update right here. So there's an easy way, just with a little copying and pasting, I can fix this. What I want to do is I'm going to move my f list sub I to be in a comma after this. So the two things that are going to get updated are going to be my R list and my F list. And all I'm going to do right here is I'm going to sort of stack these up vertically with one another. And what I need to do is, just because technically right here I should just be doing a comma and the whole thing should be carrying on, but you should notice right here Python gets really upset if you do your indentations wrong, and it's like, why did you hit enter right here? It really wants this to now be one gigantically long line. And I hate doing lines that are longer than my screen is ever going to be able to show. So instead right here, the trick with that is you can just do a slash right there. It has to be that direction of slash. The other one is a division symbol, right? That's our backslash right there. I never remember which one's back or forward slash. Anyway, the one that goes upper left to lower right there. And that says, hey, your next line is really a continuation of the previous line. So that's a Python thing, not a math thing. But again, the important thing here is we want to do a simultaneous update of the values in the R list. R list and F list to make sure they are both referencing the same one step previous in time, rather than R list getting updated and then F being using that new R value. That would be a problem for us because R got updated. F's update would then be based on the new R rather than the same time frame as was used for the previous R that's out there. So we want to do this simultaneously updating. So this says update the ith value of the R list and the ith value of the F list and use these two numbers. That's going to evaluate to a number, comma, this is going to evaluate to the number that we'll use for the F list. And the only thing that slash is doing is it's not doing division. That's just our line break symbol. That just says keep the next line stuff, it's really on this same line. I'm just writing it on two lines for visual convenience right there. All right. Now when we go ahead and we run this guy, it's, oh wait, unexpected symbol after the line continuation character. Okay, notice even, so the one thing, and Python, as I shouted at you guys before, Python is a super generally friendly language to learn at first. We're doing some kind of difficult stuff with it right now. The one thing that Python is not friendly about is spacing. But the reason it's so aggressive about spacing is because it wants you to write code that other people are going to be able to read well. It's forcing you to be a good communicator is what that spacing rules are doing. So even just putting a space right there made it get angry. And by getting rid of the space after, once you get a line continuation character, apparently there has to be nothing after it, just going on to the next line. And then it was happy with that right there. So I think that this kind of worked, right? Let's at least like look at some initial values right here and see if this seems at least like some stuff we're expecting. And yeah, these seem like believable values to me that we started our rabbit list at 1. And because we're going in such small time increments, 0.001, I'm not expecting it to change significantly each step of time. So it's not like I'm looking at those numbers being like, oh, yep, it's right. But I'm seeing like, I don't see like 4,000 out here or a negative number or ones all the way across or something like that. Like I don't see any red flags is all I'm really saying right here. This seems believable to me that this might be legit. The good news is the reason that we're doing this problem first is because we've already seen what the graph of this looks like in the phase plane. So once we graph this thing in a moment here, I'm going to feel either good or bad about the math that we've done here. All right. So a lot of things so far. Let's go see if we feel actually good about this by kind of checking out our graph of this guy. So let's just do our most basic thing, but we're going to, like I said, we're going to emphasize a little bit more graphical stuff here today. So I'm going to show you guys some more cool graphical things that we can do. And then the other thing that you guys know is we really want to make 2 different graphs. One graph is going to be R versus F. Another graph is going to have 2 graphs on it, T versus R and T versus F, our individual graphs of the individual parameterized solutions, right? So as just my most basic graph, let's just do plot dot plot. So PLT is referencing the matplotlib library. That's the alias we gave to it. PLOT is the plot function that is contained within the plotting library. So those are close to each other, but technically serving wildly different purposes. So just as my most basic plot that I could possibly do here, R list comma F list. So that's my X values and my Y values. And then let's show the graph that gets produced from this and see if it looks like we should believe the stuff that happened right there. And hey, that looks kind of believable to me from the graphs that I had seen before. I think that we should, I'm pretty unhappy that this thing, so notice by the way, it started at 1.5, although I can't even tell from the graph that that's where it started. I could be convinced that that's where it started. So we're going to want to add that little green dot for our starting location. I'm unhappy that this didn't seem to complete one of the cycles that I was sort of anticipating it completing. So maybe we should go up here and say, hey, listen, let's do this for more time. This is one of the functions that I wish that I could control. I shouldn't call it a function. That's one of the parameters I really wish I could control over at Bluffton that we can't. It drives me nuts that when we increase over here our H value, our time step to be much, much smaller, that then it just gives us these tiny little strips of graph right here. What I want to be able to say is, we'll do it for longer, man. And I don't see any way that I could modify that over here, right? So this is one big step up for us, is that we can now just say, make it go as long as we want to go with however small of a step size we want to make it. This is a very limiting thing for me, that if I want to get high precision, I have to live with super, super short chunks that don't tell me any long story out there, right? So that's not cool. So we can now control this. So I just changed 3 to 5 right here is the only thing I did. I know that I never used this number directly. I used capital T everywhere it was referenced in my code. So I should just be able to rerun the code, rerun the code, rerun the code. And oh, look, now it's giving us these more oval type shapes that we were getting from that Bluffton thing before right there, right? So I feel a little bit better about that. That's pretty nice right there. Now, if you're looking real carefully, what you should be able to see down here is some overlap. Very careful. You've got, if your screen is blurry at all, you probably can't even tell, right? But if you can kind of see this, it looks like one line thickness right here, but you should see that it looks ever so slightly thicker. And again, I'm not even sure that you can see this watching this on the video afterwards, but it seems like this is however long it took us to do like sort of one cycle, and then it kept on going for a little bit longer of a cycle right here. But the fact that it seems a little thicker to me right there says it doesn't seem like this curve like landed back on itself exactly again. It must have been like slightly disjoint so that it visually looks like a thicker single line, because it's really 2 lines that are really, really close together. So I'm immediately like, oh, I'm a little unhappy about that right there, but maybe we'll be able to fix that. Maybe that's just the nature of this system right here. So again, our absolutely most basic plotting is this right here. I want to do a lot more stuff other than just this right here. So let's go ahead and add a bunch of plotting components to this stuff. So I want to maybe make a markdown cell that says just here, like plotting our solutions. Right? So let's add a whole bunch of components. Basically what I know is plot.show. The last thing I want to do is show the graphs that I've made. So that's going to always be my last line. Um, it seems like this R list and F list is going to be kind of the first thing that we're going to start with right here. Yeah, Robot Ninja. Julia Python MATLAB. I think that MATLAB has been destroyed by Python having NumPy, and I do think that Julia does some things slightly nicer, but I think that learning narrowly focused languages is for things like graduate school rather than learning your first programming look at anything. Python is going to be always pretty easy for us to learn as an initial language here. So some other things I want to see on this graph right here, right? We've got our most basic graph. What are some other things that we want to do? Well, one thing I want to do is I want to throw in a point at my initial condition. So let's go ahead and plot the initial condition. And so to plot the point at the initial condition, we can do a plot.plot for R0 and F0. That's just one number and one number each. So it's just going to put a point there. I'm going to make my initial condition a green dot, and that's my abbreviation, my little shorthand that I can use in association with that guy. And let me just see what this looks like when I do this. Okay, it technically did it, but that green dot is really, really small. I think I want to make it a little bit bigger. So let's make the marker size be like 15. I think the default is 5. If we want you, whatever, make it bigger, smaller, whatever makes you happy right there. I think we did this stupid one yesterday. If you make it gigantic, there's your dot right there. Obviously, that's not helpful, right? So make it some moderate size. That helps me visually see where we're at right there. What other things do we want to do? Let's also throw in here, let's plot the non-trivial equilibria. So we knew that that one was at 10/9, 5/3. That's what we had previously computed. I'll make that a black dot. By the way, black and blue are two commonly used colors that both start with B. It's very typical in lots of programming language that a single letter abbreviation for black is K, because B is typically used for blue. And again, I've kind of learned my lesson now with the marker size. I think I will probably make all of my individual points be of size 15. And there is that, that point that we're looking at right there. So that makes me kind of happy. Some other things that I'm thinking that I want to add to this graph. One, I kind of like having a grid on this graph right here. So another thing I think I'll do is plot.grid, and you just got to throw true in here, and true has to be capitalized. Notice it's green, which means Python recognizes it as a keyword. If you make it lowercase t, then it's black. It's not recognized as anything special. But this will give us that background grid right there, which is pretty nice. Let's see, what other things do we want right here? Well, some other things that I'm kind of thinking that I want for myself right here are some labels on my axes right here. So another thing we can do is add axes, labels, and title. And so let's do a plot dot, and we can do an X label and a Y label. X label, what are we even graphing on the X axis right here? We're graphing the rabbit populations. So let's just see if this works. Yeah, now it says rabbit population down there. We can do a similar thing here for the Y stuff, plot.y label. And that's going to give me a fox population. And we can also do a plot.title. And we can say our newtons. So notice a thing right here. Notice that the letter turned black. That was immediately a key to me that trying to use that apostrophe for newtons right there. It actually ended the string because strings in Python are denoted by a quote or a double quote. I typically use single quotes because I'm lazy. Here, clearly, we want to use a double quote so that it knows that that single quote is just an apostrophe in there. So I'm going to do, say, Newton's method approximation. By the way, if you're looking directly above my head, you should see that next up we're going to hit the Runge-Kutta approximation. So it matters that I say what technique am I using to produce these solutions right here, because that will eventually change. So my Newton's method approximation right there. We got our rabbit and our fox population. I'm feeling pretty good about this. What other things do I want to include in here? Oh, wait a minute. Do I keep on saying Newton's method? Aren't we doing, isn't this Euler's method? Am I confusing my names right here? Why am I confusing myself with this guy right here? Newton's method is for, oh my gosh, I've been referencing the wrong smart dude this whole time. This is Euler. What am I doing? Holy cow. Newton's method is for root finding. I got to change all my stuff right here. Oh my gosh. Oh my gosh. What's wrong with me? Do Euler's method. Euler's method. Jeez, that's embarrassing. Okay. Now that I referenced the correct smart dude from 400 years ago, oh goodness gracious, got my wrong section titles right here. My goodness, now I got to change it everywhere. This is now driving me nuts. Yikes. Okay. Now that I know what I'm talking about here. So this is one good graph for us right here. But remember, the other thing that we're interested in here is producing our individual solution graphs as well. And I don't want to have to completely separate these ideas from one another. So the other thing that I'm interested in doing here is producing sort of simultaneously a second graph. It would be really cool if just when I hit Shift Enter right here, a whole second graph popped up underneath this guy right here. So what I'm going to do is this to kind of handle that type of stuff right here. What I'm going to do is I'm going to add a line of code to indicate that we really want two subplots in the total plot that we're producing right here. So one thing I'm going to do is up above my R list, I'm going to do plot.subplot. And I'm going to tell it it's subplot 1. And the reason I have to indicate this is because I'm about to ask it to make me two plots at the same time right here. Oh wait, sorry, I did that not quite right. This should be plot.figure. Plot.figure1. Now what I can do is this, so this says it knows that all of the instructions that it's getting after this are going to be tied to whatever figure 1 is. The next thing I can do down here is I can say, now let's build the individual solution graphs as the second subplot. So now I'm going to do plots.figure2. And now it's going to know that all the upcoming commands that are after this line right here are all going to be tied to some second plot. The other thing I need to tell it is where to locate it. This is our plot.subplot command. This is an aggressive shorthand right here. This is saying there should be, this is one row, first row, wait, number of rows, number of, I do get confused about this guy right here, but what I know is that that 1 is saying the index 1 location. I feel like this should be 1, 2, 1, but that gives me a funky looking graph right here. I would just say this is telling us, tells matplotlib where to put the second one. Right? And where this is going to end up putting it is going to be right below, because that one says that index 1, where index 0 is the first one, index 1 is the second. But I know that this should be number of rows and number of columns for the first two, so I feel like our code right here should be 1, 2, 1. And that gives me a funnier looking graph that I don't like, so I'm not going to do that right now. So I know that the 1, 1, 1 is going to make the picture that I want right here. So what do we want in our whole second graph out here now? Well, in our whole second graph, I want two graphs on it, right? I want T versus rabbits, T versus foxes. So let's do that. Plot.plot. I want my T lists. I want my R lists. I'm going to want to make this, let's make this, I don't know, we want to give it like a label, right? I guess I don't need anything else right here. We want to label this as being our rabbits. And very similarly, plot.plot, we want T list flist and label for the key as foxes. I know that I'm going to want to turn on a legend. I also want to get my grid on here because I prefer to see the grid. That's certainly an aesthetic choice that you can make right here, but legend is more of like a responsibility than an aesthetic preference. I'm bothered by the fact that plot.grid requires true to turn it on, but plot.legend doesn't require anything to turn it on. It just blanks inside the parentheses right there. That's always a bit of a weird thing to me. And so let's go ahead and take a look and see what this looks like now. So I don't see anything different, but until I scroll down, oh yeah, ooh, I can see, ooh, interesting right here. So I am seeing these sort of like sinusoidal curves that I was expecting to see right here. One thing that immediately bothers me about this is that I don't see any reason for this x-axis to not start at 0. So I think that one of the things that we should do for ourselves is manually control. Notice it's just picking x and y axes bounds for us. I kind of don't like that right here, especially if we pick some other initial condition that we might start at. And so by the way, like let's just go up and change our initial conditions and rerun all this stuff. Let's just do 1, 1 and see what we get. Rerun, rerun, rerun. Okay, we're getting that eggier shape when we pick 1, 1, by the way. I think that that was something that we'd seen before. And now I do see our solution curves are kind of looking like we'd seen before with those sort of overlaying, vaguely sinusoidal, because this is vaguely circular right there, right? This is as close to being a sine or cosine as this is to being a circle right there, I would say, right? But I feel like I want to play around with my axes a little bit right here. So we can also do plot dot axes. And what this wants to take in is x lower bound, x upper bound, y lower bound, y upper bound. So I'm going to give those values here. I'm thinking to myself, I want this to start at 0, and I want this to just go up to whatever our capital T time was, so I can see the whole thing out there, right? So my x values should be 0 to t. And I don't really know what to expect for my y values, but I don't really expect anything to get too massive out there. So maybe we just go like 0 to 5. That one I'm sort of guessing on. But this is x min, x max, y min, y max. That's our structure of that input that we threw in right there. And now if I adjust that a little bit, wait, why did it, well, that one didn't work out that great right there. Why did that do? Oh. Not axes, axis. Typo on my part right there. There we go. Now I've manually controlled what these are going to be. I did change that to 5, although that seems fine right there, right? So now I can see my individual solutions. I can see that they both at time t equals 0 have a time of 0, and I can see that they have population sizes of time 1. So maybe, by the way, we should do more plot dot x label here. Time and population sizes. And because we're measuring both populations, and this was our big improvement over this guy right here, was I despise this non-matching y-axis where you have to read one y-axis in red and one y-axis in blue. I can't wrap my head around that right there. Now, I wish I had these dots right here, but that takes a bit of a fancier plotting library that we're not going to use here. So in any event, I'm pretty happy overall with these graphs right here. And I want to show you guys some funky things that make me less happy about this. What we're doing right now is we're doing a whole heck of a lot of work with this really small time step right here. What happens if we try and get away with doing a little bit less work? I'm going to make this only 0.01. Ooh. It seems like these didn't come around to match back up with each other again. And by the way, if you want to feel even more unsatisfied about this, we're only doing this for 5 total units of time. Let's go 100 units of time. Rerun. Oh man. So I can't see the distinction in this graph out here. This is helpful for me seeing maybe if I asked you, at time, when the fox population was size 6, what was the rabbit population or something? You can answer that from this graph easily right here. This is concerning to me. This seems to me like from our initial condition at 1, 1, it seems like our populations are kind of getting bigger and smaller, but are blowing up to where they're experiencing more and more extreme maxes and more extreme minimums right here. It's not clear to me that this is appropriate behavior for this graph. So again, what we know is that we're going to get increased accuracy by making our dt value, truly is our delta t, much smaller. So maybe I make my step size super duper small. You should notice right now, we're doing 100 divided by 0.0001 steps. Is that a million steps, I think, right there, right? So this should take a hot minute for it to calculate this thing right here, right? That's just defining our parameters. Watch this guy should be an asterisk for a while right here because it's now got to do a million steps through this for loop here. It's computing. Oh, there we go. It's done. So it took it more than a second to do that, which is kind of a long time in computer time. Now this also is going to take a long time because it's technically plotting a million points and drawing little connections between them. So this is also, okay, that was a pretty quick one still. But notice right here, I'm still getting this like really thick line right now because this is really like lines that are very, very close to each other. And so I still feel like I'm seeing this like bit of like spiraling action here. And it's like, I don't really know if that's truly representative of what the system should actually be doing. So the question that I still have after doing all this stuff right here is, if we could actually solve this differential equation, which we can't, if we could, should we be finding our exact solutions to truly be closed orbit solutions, or should they be doing some form of spiraling here? And what I'm finding is that it's difficult for me to make that judgment call just by looking at an Euler's method, not Newton's method, approximation of the solutions right here. So where I kind of want to go with this graph from this point right here, I'm trying to see, is there anything else I want to do with this guy? No, I think we kind of did this. And so all of our graphing stuff here, right, we made two different figures in the overall plot. One was our R versus T. One was our T versus R and T versus F together. By using plot.figure1 and plot.figure2, we told it which ones should it be thinking about. This line of code told us where to put it. And by the way, notice if I do 2 right here, it will work. But for some reason, it like smashes it up like that. And I don't really know why it's doing that to me right there. And that just bothers me. So anyway, I go back to just making that 1. And for some reason, it comes out slightly nice right there. So that's one of those lines of code that I've learned to like use without 100% understanding, because the amount of time it apparently will take me to understand it is not worth the extra value that I get. Plotting stuff is very specific to this one library, not about Python in general. So we plotted the two curves. There's the two curves, the rabbit and the fox curve. Adding on these labels is what told the legend how to make that. The legend then looked for all of the defined labels, and it just made those labels happen for us right there. Right. This plot.axis is a line of code that we can use to modify manually the bounds. So this is just like in your TI calculator, x min, x max, y min, y max. It just wants that as a list. So notice that plot.axis only takes in a single object, a list. The list needs to have 4 things in it, the 4 boundaries that we're including right there. So those brackets are required. The axis command expects 1 input, a list. The list needs to have 4 numbers in it. And we put some labels on there because we're responsible graphers out here. And then plot.show, always the last command to actually produce the plots rather than just create them, to show them to us. So I want to look at one other example here today because I'm bothered by this. Is it a closed orbit or not? And should we trust Euler's method or not to show us truly a closed orbit? Because I'm still suspicious about this type of bound right here. Okay, I lied. I want to show you one more thing with this guy right here, which is in your homework from our last week, there's a question about like the paradoxical effect of using pesticides on bugs. And I think we can kind of see that by modifying our initial conditions right here. I'm going to make one of these parameters small. I played around with this a little bit earlier and I saw that like 0.35 rather than 1 made this work out slightly nicer. So again, the whole beauty of using it this way is that I don't have to change anything else. It's going to automatically redo all of our work right here. I think I can back off a smidge on some of these values right here. Maybe we don't need to go so far. So I'm doing 1/100th the work right now. I got rid of a factor of 10 each from T and DT. So now when I plot my solutions right here, notice the thing that's happening now is that if we crush one of our populations down to being very, very small, then what's going to happen is it's going to kill off all the things that used to eat it, right? So if our rabbit population got to be, so you might consider this location right over here, if our rabbit population gets small, it kills off all the foxes. Well, what happens when the foxes are gone? There's no foxes to eat the rabbits, and then the fox population actually blows up. So this is kind of the graph that I think of when I think of that paradoxical effect thing going on right here. And we can make this even more extreme if we want right here. I don't know, make that 2.5. And what we're seeing is that this graph is now getting more extremely close to these axes right here, but swinging out to more bigger extremes, because if we kill off all the predators, then the prey are really going to blow up until the predators have recovered enough to bring the prey back down. Then there's so many predators up here, such a large fox population, that it crushes the rabbit population down to almost 0. Look at how close this is to 0 right there. And then since there's almost no rabbits, all the foxes die off. And once there's almost no foxes, the rabbits make a recovery, right? So this paradoxical effect associated with that usage of insecticides is that if you kill most of the insects down to kill 99% of the insects, all you're really going to do is all the birds are going to die off. Once all the birds have died off, now that 1% of the insect population isn't being preyed upon at all, and it's going to blow up in size possibly to bigger than it was before. And so these are all the gigantic mistakes that humans have made thinking that we can control environments like this in the past. And that's why we don't do things like blanket insecticides. That's why we're trying to use more responsible farming practices that don't just use mountains of insecticides, because they cause lots of bigger problems for the environment than they fix in the short term out there, right? And you can notice over here our graphs get a little bit more extreme out here. Did I set that to be T? Thought I did. There we go. Now they're still creeping up over the top right now, so maybe I want to set that to be like a 10 or something like that. And now we can see this graph is on here, and we're really getting up to extremes and decaying off and spending long periods of time at almost none of the population right there as the predator population dies off, right? So really, really easy way for us to produce our own graphs that are of officially better quality than this one right here, because again, I hate these short little chunks right here. I can't control what I've referred to as capital T in the previous, in our code, in this graph right here, and that bothers me. I can't make these have matching axes, and that bothers me. And we've fixed both those problems with the graphs that we're producing right now, which does not bother me. It makes me happy. So I want to look at one other example today, and I want to complain about this closed orbit thing. So what we're going to go do is we're going to do the smart thing that we always do in math, which is let's compare our work against something that we know the correct answer to see if we, like, to what degree should we be trusting Euler's method here. So one of my issues is that we don't know enough to be able to say for sure if these methods should actually be closed orbits based on the evidence from Euler's method. All right. So let's look at a simpler problem to which we know the solution, which we don't know the analytic solution to the rabbit and fox population problem there. Let's come back to our undamped mass on a spring. Undamped meaning there's no damping force. Remember that damping force is like friction opposed motion. Motion is velocity, and you should notice that we're missing a k prime term in there. There is no velocity associated term. There's only a spring force term, kx. Springs resist position, so we have a kx in there. I'm going to let k be equal to 1 because I want to do the easy version of this problem. And so in that scenario, we have already done the conversion from the second order differential equation into a system where the derivative of position is what we call velocity. Then if I take the derivative of velocity, we know that's actually just the second derivative of position. So I just subtract 1x over to the other side to get negative x is what the derivative of velocity is. This is the second derivative of position, that's acceleration. We already guessed our way to the correct solutions on this a couple of weeks ago, right, or 2 weeks ago. We saw that using cosine and negative sign is a good parameterized solution for this system of differential equations. You should notice the derivative of x, the derivative of cosine, is v, is negative sign. Then the derivative of v, the derivative of negative sign, should be negative cosine, and we've got negative x, where that's negative cosine. So it seems like this x and v are clearly our solutions to the differential equation system right there. And the great thing is that we know that any set of combination of sine and cosine, regardless of what order it is, regardless of positive or negative, is going to parameterize a circle. This is one of your basic parameterizations that you guys learn in Calc 2, I believe. And so I know for a fact that the correct solution to this is closed orbits. I literally know the explicit analytic solution. I know it to be the parameterization of a circle. The only thing that the positive negative sine versus cosine thing modifies is where do you start on the circle and where do you, what direction do you rotate? But the graph itself should be a circle, right? So what I want to do is I want to just copy and paste basically everything that we did up above, get our new graphs back out, and look and see if Euler's method is something that we should be trusting relating to these potentially closed orbit solutions right here. So I'm going to do this in a largely copy and paste way because the whole point is we did the hard work of generating this code right here. So our functions, our library is already imported. Let's go ahead and copy and paste this structure right here, but it's way easier now, right? So instead, I'm going to define my f and g functions to be based on x and v. Those are our new variables of interest for us now. And we've got much easier definitions. Our dx dt should just be straight up v. and dv dt should be negative x, right? So this is exactly mimicking exactly this system of differential equations. So I'm going to shift enter, run that guy right there. Let's see, what's next? Next up, we want to grab our, okay, that was just a checker right there. Let's go ahead and do like our initial conditions, our time step, building our empty lists, all that good stuff right there. All right. I'm going to get rid of like all of our comments since I don't quite think that we need them. I think we've described these things up above. I kind of just want to get them all out here now. I'm going to start this thing at 1, 0. So it's on a unit circle right there. And let's not get too crazy right there with dt just yet. And again, I'm going to do our like minimized version of this right there. T-list, all that stuff is the same because it's just based on the parameters that we've selected. R-list and F-list, I'm going to rename to be X-list and V-list. Oh, that's what I got to do right here is say that's X0, that's V0. I think all that stuff seems fine right there. Let's go ahead and set our initial conditions into their appropriate lists, X-list and V-list, our X0 and V0. So I'm copying and pasting, getting rid of my fluff descriptions from up above. Comments are good. Use comments. I just already described all this code up above, which is why I'm getting rid of the comments so we have a more compact version of it right here. And I converted everything that references R and F to be X and V for our new problem here. So I'm going to run this. I see that it's not complaining at me about anything, so I'm happy for now. Let's go grab our next block of code up here. The next thing we did is we did Euler's method. We did our simultaneous update right here. So I'm going to copy and paste this for loop with a simultaneous update to do our Euler's method, not Newton's method. We're going to update our X lists and our V lists. R is what I'm calling X, V is, or F is what I'm calling V. So X then V, X then V. X gets updated as X plus, V gets updated as V plus. The dx dt is our lowercase f function. dv dt is our lowercase g function. Both of the functions that we wrote take in an x piece of information, then a v piece of information, x, then v. And we're going to do each of these for delta t, units of time. Remember that that is just our line break right there. Okay. So we've done, that just did it. That just did our like 1,000 steps, or our 1,000 steps of Euler's method right here. Now we want to go grab all of our plotting code and see what the heck this stuff looks like. So we just kind of, we're reusing the heck out of all this stuff. And notice, honestly, I could have changed way less here by literally just going up and changing just my functions and nothing else right here. Just changing these 2 lines of code. That's all you should have to do. I just don't want to delete any of this pre-existing code, which is why I'm copying and pasting it rather than just changing some of the small values right here. So again, I'm going to get rid of some of my extra stuff right here, all my comments, since this is already described up above. But we'll change all of our things as necessary right here, right? So plotting the figure 1, I want to plot my X list versus my V list. I want to plot my X initial condition and my V initial condition. I don't need to plot this guy anymore at all because that was a equilibrium that's not associated with this problem right here. So I'm just going to get rid of that. Our X label should now be our position. Our V label, which is technically our y-axis, should be velocity. This is still an Euler's method approximation, and that should give us our first graph. Our second graph is still going to be figure 2, still going to be the same location. Still want to use the t-list, but I want to use the t-list with my x-list, and this is going to be position. Still want to use my t-list, but that's in conjunction with the v-list. That should be my velocity. Still want to turn on a grid. Still want to put a legend on there. I'm a little less confident about this axis formation right there. So I'm just going to, so notice if you want to turn a line of code off in a sense, you can just make it a comment. And now if I decide I want that back, I just got to go get rid of that thing right there. So this is the way to like kind of hold off on that for a second right there, saying I'm not sure if I want to manually adjust the axes like that again. And in the second figure, it is time that's changing right here. And over here, I might just say position and velocity. And so let's go take a look and see what we see out here. So here's the deal. This makes me happy. This looks like my sine and cosine graphs, right? Like I'm pretty pumped about this guy right here. It's hard for me to tell in this graph that these are not perfectly coming back around to repeat themselves, which is what I'm seeing here. Now, one of my issues right now is that I am dissatisfied that this graph didn't give me a true circle. And the reason that it didn't is because it looks like this plot is set up to have dimensions of like 4 by 3 or something like that for the default. I don't like that. I want to change like literally the box shape. And it's not like this is going from like, -1 to 1 and -1 to 1 as the axes bounds. Like the X-min, X-max, Y-min, Y-max are both -1 to 1, -1 to 1, or close to that. But the like figure itself is not a square. So that's actually something that we can change up here. When we do plot.figure1, our first figure is this plot. I can tell it what I want the dimensions of the actual like canvas it's writing on to be right here. And so here I can do fig size equals, and I don't know, like just something that's the same number on both of them right there, right? So if I do like 10, 10, okay, that's bigger than I need that to be right there, but it's big now. I'm seeing circles, right? I think 10, 10 is a bit overkill right there. How about like 6, 6? Okay, that seems reasonable to me relative to the size of this guy right there. So by doing a fig size argument within plot.figure, we can change that. And again, if we wanted to do something like really stupid, like 2, 9, then we could get a obnoxiously shaped graph that's 2 units wide and 9 units tall. That's obviously not what I want right there, but that's just kind of how that works right there. So 6, 6, I think made me happy right there. But the thing again that makes me unhappy is I know for a fact we have done this. We've found the analytic solution. This should truly be a true circle. So the thing that I'm recognizing now is this, basically. This is kind of our takeaway from this. Every time we're finding our numerical solutions, what we cannot do is guarantee that things that look like closed orbits are in fact closed orbits, or things that don't look like closed orbits. Like this looks like it's spiraling, but I know for a fact that it's not. We've done this. We've solved this differential equation. We've got the true solutions. These parameterize a circle, right? So I want to show you that like we could do this for 100 units of time instead, rerun all of our code. Like I know that that's not the action. I know it. That's not the parameterization of a circle. So what do we need to do? Everything we always do in calculus. Limit towards infinity, or in our case, infinitely small step sizes out there. So if I instead make this 0 go to 0.001, ooh, we're getting there. This is it, just like sort of drawing like adjacent to the curves right there. And now we can go real small in this. Now this is another one where we should expect this to take like non-zero time right here. Oh, hey, that was still really fast. Okay, we're getting closer and closer, right? So if you can do your limiting, and this is like literally your limit as h approaches 0 is literally what we're doing right now for our limit definition of the derivative, right? So maybe here's what I should do is, if that one went as fast as it did, let's go even smaller on dt here. I'm sure this is going to take it a moment to do the count and notice all these stars stacking up are saying, I'm thinking, man, give me a break right here. This is where all the heavy work is happening. This is actually the Euler's method happening right here. Right now, we're setting this up to do what, like 1 million or 10 million steps of Euler's method. It's not going to take 0 time right there. So we're, oh, okay, it finished doing the calculations, but now plotting it. It's got to plot that 1 million or 10 million things. But notice, we're now still seeing a slightly thicker curve. Oh man, literally large amounts of data. Creating legend can be slow with large amounts of data. I think, by the way, this is just a warning. So I think did it just do it? No. Is it still thinking? It's still thinking. So this does not say error. This is a warning. So this is being like, dude, you maybe shouldn't be doing this right now. If we were being smarter, we would maybe just take like a sample of every 100th point, because the points have been computed properly according to Newton's method, but like if we took every 100th point, these points are so close together that even by taking every 100th point, we're still going to get a relatively smooth curve. The other thing that I think that you guys should be sort of impressed by in the sense right here is, and now it's really hard to tell on this right here, this is obviously just a sine graph that's been, in a sense, compressed right there. But are you guys not kind of impressed that we produced essentially a perfect sine and cosine graph without ever using a sine or cosine function? I hope that you are, because I think that that's super cool right here. I'm not terribly surprised that we produced a solution that's exactly like a circle right here, but the fact that we were able to get an exact sine and cosine curve right here, and we've never typed in sine or cosine. We never said graph sine or cosine. This is just what you get from doing the Newton's method approximation. Oh my gosh, the Euler's method approximation associated with this differential equation. So you should see that like this sine and cosine are sort of like inherently defined associated with this differential equation right here. That is just a consequence of performing Euler's method on this differential equation. We never ever actually came up with sine or cosine. It just emerged from our solutions right here. And that's actually pretty cool. So now you should be saying things to yourself like, when I ask my calculator, what's the sine of 14.11 degrees? Do you really think that it has a function that's truly computing sine values? Or do you maybe think that it's doing something more like an approximation like we're doing right here and just getting an excellent numerical approximation for it? So that's actually a really handy thing to see. So I think this was crazy of us to do that much right there. So I'm going to back off only 1/100th of what we were doing before. And I'm pretty happy with seeing that this is like yeah, and the question I'm seeing here in chat is, I wonder how Euler did this stuff before Wolfram Alpha. This is genius. And again, the idea here is like wildly simple in that all Newton's, oh my gosh, how many times am I going to say the wrong thing? All Euler's method is literally y equals mx plus b. That's all that's happening. This is literally just y equals mx plus b. But you're totally right that like did Euler ever practically use this for a good practical purpose? And my answer is I really don't know. What I imagine is that back in the day, being a graduate student studying under Euler meant that he handed you a piece of paper and said, hey, go ahead with dt being 0.01, run this out to time 5 for me. And you would just sit down for a week and do by hand calculations and come back to him and be like, I hope I didn't make an error on step 6, or else it's propagated throughout the whole dang thing. So I think that he had a number of people beneath him to where that was what math used to be, was just do a week's worth of calculations for one problem. But again, like, this is one of those moments where I have a hard time saying to myself things like, thank goodness it's the year 2020 or 2021. But in this context, I'm pretty pumped about it because we're literally busting out millions of calculations in like seconds right here, as opposed to it taking weeks for an army of educated people. And so the fact of the matter is the ideas behind these are easy, but the practicality behind these ideas was not realized for 90% of the time since Euler's method has existed. I mean, this came up in like 1670, he figured this stuff out. This wasn't practical till 1970. And even then, we're talking about you having to like take multiple classes to learn enough programming to reserve a computer that took up an entire, these are my dad's stories about doing this when he was an engineering major at Marquette University. Engineering, not any one of the 50 subclasses of engineering that you now get degrees in. My dad has a degree in engineering, and there was a computer that took an entire floor. One computer took up an entire floor of the engineering building, and you had to reserve time on the computer to run your punch card code that looked like it was a sheets of paper that you would punch out squares in a grid, and that's how your code would be run. And so because it was such a highly valuable computer to use, it was 24 hours a day, 7 days a week that you could reserve time. And if you're only a sophomore instead of a graduate student, you're not getting the good times. So my dad would manage to reserve like 2 a.m. to 4 a.m. on a Wednesday, on a Wednesday night or something like that. Well, what do you do if you're just waiting around until 2 a.m. to do something? So my dad's just sitting at the bar waiting until 2 a.m. to roll around because he's a sophomore in college. It's what you do. And so his story about him learning computer programming is you spend a week converting your program that does nothing even remotely as complicated as what we're doing right now. And then he's walking up the flight of stairs to get to the computer, and he's drunk, and he dropped his stack of note cards. And so now he's got, there's like 200 note cards that he has meticulously punched out and put in an order. And he's like, shit. And so he then had to just whiff on his computer time, spend another 2 hours finding the new ordering for all of his cards again, re-reserving new time for the computer, getting an extension on the assignment, all this business. feel some appreciation for where we're at right now that we can do this stuff. Like I am happy that I don't have to relive punch card issues like my. And then if you get an issue, how do you debug that program? No idea. Yeah, I agree with you, RGPT. I would be following in my dad's footsteps if I were in his same shoes right there. I don't think I'd be doing anything different. I think my story would be identical if we never graduated on from that to these much nicer things that we can do here. So we still recognize that Euler's method is still, it's just an approximation, and so we're still going to get those like bad approximations that look like spirals when they're really not. So we still need to know enough math to know to like maybe distrust the graphs that we're seeing produced here, to say, well, that's just an approximation, and because we're following these vectors that are always going to, in a sense, fall outside of the circle, we see this spiraling outward behavior that is an artifact of the linear approximation technique that is not representative of the true solution right here. And again, take a moment to be very impressed that we just managed to produce almost perfect sine and cosine graphs without ever using a sine or cosine function, because they are inherent in the solutions of this differential equation right here. So these are going to be some of the things that we're going to talk about here coming up. In the homework, I'm going to ask you guys to produce some graphs of some differential equations. And the nice thing is going to be is that if you've got this code right here, all you should be having to do is just change these two things right here is all you have to change. And then potentially changing your initial conditions, your dt and your t right there. All the rest of this code is completely unchanged, except for potentially you modifying your axis to make the visualization slightly nicer. You're going to get your two good graphs right there. So in my mind, this should be just as easy for you to constantly reuse this as a total replacement to our Bluffton over here, because I hate these short little pieces of graph that I cannot make longer right here. I want a capital T to control the duration of time, and we don't have that. I want a consistent y-axis over here, and we don't have that. Now we do. So you should get this code working on your own machine right here, and these lines right here are the only thing that you basically ever need to modify, and this is now going to be your working grapher for all of your solutions to second orders and your systems of differential equations, whether you can find an analytic solution or not. You now control the mechanics of producing these graphs right here. So powerful stuff right here. So where we're headed with this stuff next week is we're going to see the Runge-Kutta method. Right now we're doing Euler's method, which is a linear approximation. The Runge-Kutta method is going to say maybe we should consider more than just the one previous point to make our update right there. And so the Runge-Kutta method is, and as you guys have seen, it's referred to, if we go over here, it's referred to as the Runge-Kutta 4, RK4. That's because we're going to use 4 previous points information to compute the next points piece of information. More information means we're going to get better, more accurate predictions. And what we're going to end up finding is that the Runge-Kutta 4 method, when we use this same dt of 0.01, we're going to see literally no spiraling or even like that thicker line from the overlap. It's going to be like almost perfect right there. The RK4 method is going to be a greater improvement right there. It's the actual technique that most people are using when they're graphing second order or systems of differential equations. So we're going to upgrade our technique next week. The other thing I'm going to show you is something that is not directly tied to our numerical solutions here, but in exactly the same way that we have this iterative process to constantly update our location, there are iterative processes to construct analytic solutions, like an actual function, rather than just iterative methods to compute numerical approximations. So we're actually going to see a way that we can use it's called Picard's method, P-I-C-A-R-D, Picard's method. And Picard's method is in the style of Euler's method, but it's actually going to iteratively construct the Taylor series of the analytic solution. So we will actually get general analytic solutions for things using an iterative method, using Picard's method right there. So that'll be another cool little topic we'll hit next week. So next week, 2 more videos, 2 more things with lots of kind of Python programming, iterative methods to produce solutions, stuff like that. So we'll improve on our stuff next week with the Runge-Kutta method. We'll look back at some of these same examples here, but now we're going to want to maybe even do like 3 graphs where we have the Euler's method solution side by side with the Runge-Kutta solution with the same parameters of t and delta t, but with a clearly better graph is what we're going to end up seeing for the Runge-Kutta. So that'll wrap it up for me here today. Thank you guys for being here in chat and making fun of me for the stupid mistakes I'm making over here. And I will see you guys for our Runga Kutta video. Oh, wait, sorry. That's not next week. Runga Kutta method, I'm going to do that guy tomorrow. It's Friday right now. I'm going to do a Saturday one since I didn't do my Thursday video yesterday. So tomorrow, I'm going to make my Runga Kutta method video out there as well. So you guys can catch me there. Have a good one, everybody.